Okay, so here in this video we're actually going to look at taking the antiderivatives of our trig functions. But before we proceed to an example, let's list the trig integrals that we have. The indefinite integral of cosine u du is equal to sine u plus c. The indefinite integral of sine u du is equal to negative cosine u plus c. And the indefinite integral of secant squared u du is equal to tangent u plus c. Over here we have the indefinite integral of cosecant squared u du, which would be negative cotangent u plus c. The indefinite integral of secant u tangent u du would be equal to secant u plus c. And the indefinite integral of cosecant u cotangent u du would be equal to negative cosecant u plus c. So we'll keep those handy throughout our examples. The first one, the indefinite integral of cosine of 2x plus 3 dx. So this form does not match exactly one of these. So we're going to do u substitution. Obviously it resembles this one the most, but it's not exactly cosine u du. So we have to choose u, again, to be the inside stuff of the function. And the inside stuff is 2x plus 3. We'll take our derivative and get du equals 2 dx. And now we're going to mold the integrand. I will put a 2 in and take out a 1/2. So then now this here would imply I'd have 1/2 times the indefinite integral of this 2 and dx would come together to become my du. So that would go. And this would be cosine, and this is u. So the indefinite integral of cosine u du would be equal to 1/2 times sine u plus c. And now substituting back in terms of x, I would have 1/2 times the sine of 2x plus 3 plus c. And it should be by no surprise that that is the most general antiderivative, because when we take this derivative, the derivative of sine is cosine, so it would be 1/2 cosine, repeat the inside stuff, plus 2x plus 3, times the derivative of the inside, which is 2. They would drop out, and the derivative of a constant is 0, and I end up with the function I have in the integrand. Another example, suppose I have the indefinite integral of secant 3x tangent 3x dx. So I would let u be equal to the inside stuff, which would be 3x. And again, after I do my u substitution and convert everything in terms of u, I have to get this in terms of one of these 6. I have to mold the integrand into one of these 6. And obviously it resembles most this one. So then the derivative here is du equals 3 dx. Put a 3 in and take out a 1/3. So then now this would become 1/3 times the indefinite integral of 3 dx would become my du. And this would become secant u tangent u. And this is on my list of 6 up here. So the antiderivative of secant tangent is secant u plus c. And this would become 1/3 secant of 3x plus c. And again, the derivative of this function, well, that would be 1/3 secant 3x tangent 3x times 3 plus 0. These drop out. I end up with the function in the integrand, which is right here. Okay. Next, let's take a look at, suppose we have the indefinite integral of 2x cubed times cosine of x to the 4th dx. So again, try letting u be equal to the inside stuff of a function. So my function is cosine. Its argument is x to the fourth, the inside stuff. So u would be equal to x to the fourth, and du would be equal to 4x cubed dx. So it looks good because I have an x cubed dx present in the integrand. So I can just take out that constant 2 in front. So it'd be 2 times the indefinite integral of, I'll put a 4 in, make this 4x cubed, and just rewriting it, cosine of x to the fourth dx. And if I put in a 4, I have to take out a 1/4 to be fair. So then that you could picture these dropping out and this becoming 2x cubed times cosine of x to the fourth dx. Now in terms of u, this would reduce to 1/2 times the indefinite integral of the 4x cubed dx would all become my du from over here. And this would be then the cosine of u. And the indefinite integral of cosine u, what function has a derivative of cosine? Well, that's sine. So it would be 1/2 sine u plus c. And this would be 1/2 sine of u, which is x to the fourth plus c. And again, to check yourself, you can just take the derivative. Next, another example. Suppose we are given the indefinite integral of secant squared root x all over root x dx. So again, obviously this looks most likely it's going to take on this form right here, secant squared u du. So we have to mold the integrand to get in this form. We have to mold this right here into that form. So try letting u be equal to the inside stuff, that is root x. This is also x to the 1/2. Its derivative du is equal to 1/2 x to the negative 1/2 dx, or 1 over 2 root x dx. So du equals 1 over 2 root x dx. I do have a 1 over root x dx in the integrand, so this looks good, provided I put in a 1/2 and take out its reciprocal, which is a 2. So this would translate into 2 times the indefinite integral of. All of this would become my du, and this would become secant squared u. And what function has a derivative of secant squared u? Well, it's tangent u. So this equals 2 tangent u plus c. So this is 2 tangent of root x plus c. And there's my most general antiderivative. Next, how about if we're given the indefinite integral of x times cosine of x squared cotangent of x squared dx. So hopefully it looks like we will mold the integrand into probably this form, cosecant cotangent. So try letting u be equal to x squared. Du equals 2x dx. I have an x dx in my integrand, so I'll put in a 2 and take out a 1/2. And this would become 1/2 times the indefinite integral of cosecant u cotangent u, because this is u, and this become my du. And the indefinite integral of cosecant u cotangent u du is negative cosecant u plus c. When the answer to an antiderivative is a c function, the result is negative. The answer to an antiderivative when it's a c function, it's negative. So then be negative 1/2 cosecant of x squared plus c. Okay. Another example. Suppose we have the indefinite integral of secant 3x tangent 3x dx. So it looks like it's going to be of this form. So if I let u be equal to 3x, du would be equal to 3 dx. Put a 3 in, take out a 1/3. So then now this would become 1/3 the indefinite integral of this, and this would become my du. And this would become secant u, tangent u, because u is 3x. So this becomes a u, this becomes a u, and now I have secant u, tangent u, du. And that would become 1/3 secant u plus c. The derivative of secant is secant tangent, so this is a valid antiderivative. So now in terms of x, it's 1/3 secant 3x plus c. Okay. Next, just a little more on the variety of these that can happen. Suppose we have the indefinite integral of sine of 1 over x all over x squared dx. So it's not one of these 6 forms exactly, so we have to mold it into one of these 6. So I'll let u be equal to the inside stuff, which is 1 over x, which you know is x to the negative first. The derivative du equals, drop this power down, negative x, decrease it by 1. You're taking a derivative, so you decrease it by 1 dx. And that translates into that du is negative 1 over x squared dx. So it looks good. I have 1 over x squared dx in the integrand. So I'll put in a negative and take 1 out so that I can now substitute. This would become the negative indefinite integral of sine u. And this, with all of this, becomes my du. And this is obviously right up here. So the antiderivative of sine is negative cosine u plus c, because when the answer is a c function, it's a negative answer. But a negative times a negative is a positive, so cosine u plus c is my answer. Now in terms of x, it would become the cosine of 1 over x plus c. Okay, and another example, 2 more, where this happens. The indefinite integral of sine of x over 2 plus the cosine of x over 3 dx. When you have an indefinite integral of a sum or a difference, you can split this up at the plus or the minus sign. Never of a product or a quotient, but you can split this up at the plus or the minus sign. So this would become the indefinite integral of sine of x over 2 dx plus the indefinite integral of cosine of x over 3 dx. So once again, I'll let u be equal to x over 2, which is the same thing as 1/2 x. The derivative du equals 1/2 dx. I'll put in a 1/2 and take out a 2. Over here, I'll let u be equal to x over 3, which is the same thing as 1/3 x. Du would be equal to 1/3 dx. So I'll put in a 1/3 and take out a 3. So all of this will become 2 times the indefinite integral of this and this will all become my du times the sine of u plus 3 times the indefinite integral of this and this together will become my du, and this will become the cosine u, indefinite integral of cosine u. So then the antiderivative of sine u is cosine u, but because the answer is a c function, it's negative. So it's negative 2 cosine u plus the antiderivative of cosine is sine, so it'd be 3 sine u plus c. And now substituting these all back into here, this would be negative 2 cosine of the u here for this piece is x over 2 plus 3 times the sine of the u for this piece is x over 3 plus c. And if you haven't realized the pattern with these, that the derivative here is 1/2. So that means the antiderivative will contain a factor of its reciprocal, which is 2. Notice here the derivative will entail 1/3, so its antiderivative will have a factor of its reciprocal, which is 3, as a little shortcut. You can visually see that the derivative of 1/2 x is 1/2, so its antiderivative will contain its reciprocal, which is 2. The antiderivative, the derivative of 1/3 x is 1/3, so its antiderivative will have a factor of its reciprocal, which is 3. What does that do for you? Well, if you were to do real quickly the antiderivative of cosine 4x dx, you could see that by letting u be equal to 4x, du is equal to 4 dx. Put a 4 in, take out a 1/4. The reciprocal of the derivative is 1/4 times the indefinite integral of cosine u du, and that would become then 1/4 sine of 4x plus c. That the reciprocal of the derivative of 4x is 1/4, and that's what's contained in the antiderivative. The derivative of 4x is 4, its reciprocal is 1/4, which is now contained as a factor in the antiderivative. And just one more, what if we had one that was not off the list, but we could still work with it? The indefinite integral of the quantity secant squared x plus 1 dx. Well, here you cannot choose u to be equal to x plus 1 because the x plus 1 is not a part of this argument. It is strictly secant squared x plus 1. So again, as I said earlier, split up the indefinite integral. Split this up at the plus or the minus. So this would become the indefinite integral of secant squared x dx plus the indefinite integral of 1 dx, or just dx. And this, a function whose derivative is secant squared, is tangent x, and the antiderivative of 1 dx is just x, and finally plus c at the end as a constant. Okay, and just one more then. The indefinite integral of sine x times the cosine of cosine x dx. This is the argument of this trig function. So let u be equal to the inside stuff. So the derivative of a c function, be careful, is a negative answer. The derivative of a c function is a negative answer. So then now I'll put in a negative and take one out. And this now would become the negative. Well, this negative sine x and this dx would become my du. And this would now become cosine of u, because I let u be equal to cosine x. And this is on one of my 6 forms up here. So this would become negative sine u plus c, which is negative sine of cosine x plus c, would be the antiderivative then, the most general antiderivative. And there we have quite a few examples illustrating how to take the antiderivatives of these trig functions, where we end up in the integrand with one of these 6 forms. And again, those 6 forms represent derivatives of functions that we know.